Hello students, welcome to today's lesson. I'm Mr. Kevin Jagi from the School of Computing and Informatics. The unit is computer mathematics or computational mathematics. And in this particular unit, the objective of this unit is to understand the different numbering systems that exist, especially the ones that are used in computing. We are going to look at the decimal numbering system, the binary numbering system, the octal numbering system, and the hexadecimal numbering system. By the end of this lesson, you'll be able to understand why the computers use the binary language and how you can convert numbers into binary language the same way the computers convert from decimal to the numbering system. So our first topic is on the binary numbering system, and we are going to understand the concept of the binary numbering system from the basic and the general numbering system, which is the decimal numbering system. Binary numbering systems are numbers to base 2, which includes zeros and ones. And these are the numbers that the computers use, especially in management of data, in storage of data, in representation of data within the computing. But the decimal numbering system is the language of human being, the language that we use, which is based on base 10, from 0 to 9. So we use the decimal numbering system, and which is our common language, to understand the binary numbering system, which is the language of computers. So there are 4 common numbering systems that exist, and out of these, you can be able to form or represent numbers using other numbering systems that are not represented here. Out of these 4 major ones, you can convert a decimal number into a binary, a decimal number into an octal, a decimal number into hexadecimal, and vice versa, and still perform internumber conversions from binary to decimal, octal to decimal, octal to binary, octal to hexadecimal, and so on. So by the end of today's lesson, you'll be able to understand how each of these numbering system works and where we apply them in computing, and how to carry out calculations using this numbering system. So we'll go through each one of them, starting from the decimal numbering system, the binary numbering system, and up to hexadecimal numbering system, and try to understand each at a time. So the decimal numbering system are numbers to base 10. And we have said this is the language of human being. We count numbers from 0 to 9. A total of 10 numbers. That's why we refer to them as numbers to base 10. So any number that you can form out of these 10 numbers from 0 to 9, so long as it is under base 10, it qualifies to be a decimal number. Most people confuse a decimal number with a number with a decimal point. No. A number with a decimal point is a fractional number, which can also be a binary number, octal, or hexadecimal. So when we mention of a decimal number, this is a number to base 10. And these are examples of decimal numbers: 356 base 10, 596 base 10. It can also be a fractional decimal number: 0.762 base 10, 5.123 base 10, and so on. So these are decimal numbers. So out of the decimal numbers then, once you type a decimal number from the computer, let's say you type 4, the computer converts 4 into binary, which is the language of the computer. So later we are going to see how to convert now these decimal numbers into the binary numbers, that is zeros and ones, that the computers use. The next numbering system is the binary numbering system, or the binary numbers. The binary numbers are numbers to base 2, and there are only 2 binary digits, a 0 and 1. So any number that you form, any combination of numbers as a result of these zeros and 1, so long as it is under base 2 again, it qualifies to be a binary number. And this is the language of computers. Computers are designed to use the binary numbering system due to a number of reasons. One, if you look at the binary numbers, there are only two. And the computers are designed using components that operate in two states, which we refer to as bi-state, two states. And the binary numbers, one of the binary numbers are used to represent those two states. A 0 represents, let's say, the on state, and the 1 represents the off state, or the other way. So therefore, you are able to represent two states using these two binary digits. The capacitors, the transistors, the circuits, the diodes, they operate in two states. A circuit is either on or off, so you can represent one state with the other. The capacitors, they store charge. They either have the charge or they don't have the charge. So binary systems are used to make it easier to design computers, given that you only represent the state of the computer using two representations. Otherwise, if we use the decimal language, which is the language of computers, the one you have just mentioned, if you represent one state using one digit and the other with the other state, what will you use to represent these other numbers with? You'll end up with a computer that is very complex. So for simplicity purpose, the computers are designed using the binary system, which is just based on ones and zeros, which can also be a whole number or a fraction of binary. It can also be 0.101, it can be 11.11, and so on. So it can also be a whole number or a fractional number. And we refer to them as a 0 and a 1. We don't say 111. No, this is 111.111. This is 0.1010. This is 1010, not 1010. We refer to them as ones and zeros, which are binary numbers. We also have an octal numbering system. The octal numbering systems, these are numbers to base 8, and they consist of numbers from 0 to 7, a total of 8 numbers. So they are numbers to base 8, a total of 8 numbers. And any number that you form as a result of combination of these 8 numbers, 0 to 7, qualifies to be base 10, so to be an octal number, so long as it is under base 8. Remember, even decimal numbers from 0 to 9 consist of the same numbers, but now decimal numbers are to base 10. And octal numbers, you represent them using base 8. So any combination of those numbers from 0 to 7, so long as it is under base 8, it qualifies to be an octal number. So a number like 69 base 8 is not an octal number, because 9 is not among the octal numbers. 69 base 8 is not an octal number. 9 is not an octal number among the listing of the octal numbers. So it can also, again, be a whole number, or it can also be a fractional number, a number with a decimal point. 0.743 base 8, or it can be a whole number without a fractional part. And then lastly, we have hexadecimal numbers. These are numbers to base 16. Numbers to base 16, and they consist of numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then after 9, A, B, C, D, E, and F. Where in this case, we'll presume numbers to be 16 to be 0 to 16, but in this case, after 9, we don't use 10 as a value, because when you write 10 here, you'll have 1, 0, and you already have a 1 and a 0 represented as a separate element or separate value. So we use the alphabetical letters A, B, C, D to represent, A to represent 10, B to represent 11, 12, 13, 14, 15. So equivalent, it will be like 0 to 15, but in a total of 16 numbers, but in this case, we don't use 11, 12, and so on, because when you use 11 here, we already have 1 and 1. When you type 1, you cannot tell the computer, wait, I have another 1, I mean 11. Those are treated as separate values by a computer. So again, they can be a whole number, 7, 6, 4 is 16, or it can be a fractional number. Any combination of numbers that you form out of these values qualifies to be hexadecimal number, so long as it is again under base 16. So you can see you can form 8 A, B, base 16, A, B, C, D, base 16, C, B, 9, base 16. Any combination of numbers as a result of these 16 values, so long as it is under base 16, is an hexadecimal number. Where do we use this numbering system, especially in computing? But before we get to know where we use them, now this is the numbering system relationship. When you look at the decimal numbers from 0 all the way, you can equate them to the equivalent hexadecimal, octal, or binary. 0 equivalent to the binary 0, 0, 0, which is equivalent to the binary hexadecimal 0 and 0. Octals, we have said their numbers to base 8. So when you run them up to 0 to 7, then the next digit after 7 will be 10, because 7 plus 1 in octal is 10. The next number after 7 in octal is 10. The same way as we are going to see later in our calculation, when you are working with binary, 1 plus 1 is not 2, it is 10. It would look like 10, but it is 10. 1 plus 1 is 10, equivalent to 2, the decimal 2. As you can see here, now 2 is represented using 10. You know, when you have zeros in front of a value, it does not change the value of that number. So this is the same as 1, 2. 1 plus 1 is the same as 2, which is 10. And when you do the same throughout in this representation, again, you realize that in hexadecimal values, again, 9 plus 1 is equals to 10, which is the value A. 9 plus 1 would equal to 10, but in this case is the value A within the numbering system. So when you look at this, the relationship between the various numbering system, then you'll find it's each value and its equivalence. Where do we use this numbering system in computing? Because all of them, we use them in computing, especially the binary, the octal, and the hexadecimal. For the binary numbers, we use this to manipulate and store data. All pieces of data, whether they are numbers, whether they are words, whether they are video, data that is form of graphics, in music, they are stored using the binary system. And these computers, they operate using the binary system, the zeros and ones. The components that makes up the computer, they are based on this binary system or this binary state. Like we have said, the on and off state will be represented using the binary 0 and 1, such that each and every time the values are represented using those two states. So this one is made to simplify the design of computers and other related technologies, whether they are televisions, they are mobile phones, the tablets, portable device adapters or PDAs. They are designed using this so long as they are electronic equipments. So where, again, do we use the octal numbering system? Octal numbering systems, they are also used in computers. And they are used because they simplify the binary representation. Like we have seen in our previous diagram, when you represent the octal number, this is for the hexadecimal system, when you represent the octal number using the binary system, each octal number is represented using 3 binary digits. Like 0 will be 0, 0, 0. A number like 3 to be 0, 1, 1. So when you take 3 binary digits and then represent them using 1 octal number, you simplify the way data is represented in a computer. And therefore, octal numbers are used to simplify or to shorten the representation of binary numbers, and by grouping those values into groups of 3. That way, you'll have a lesser representation of values compared to using binary numbers all throughout. Again, some of the programs and applications, they use the octal representation, like the ch mode, which is the change mode command in Linux operating system or Unix operating system. It uses octal to assign permissions to users, especially in data and files. This file can be assigned to a particular user, and that user has which permissions? Does that user have the permission to read, to write, or to execute in terms of permissions to the users? So it uses the octal representation. Again, some systems that were designed earlier, like the universal automatic computer, the programmed data processors of the PDP, and some machines that were produced by IBM, that is the mainframe computers by the IBM, which were using the 12 bits and 24 bits and 36 bits. They were using this particular numbering system. And therefore, this particular octal abbreviation was most ideal for the representation of data in these particular computers, because the word size of these computers or these systems were represented using 3 bits representation, and therefore it was most ideal. And today we have a more modified version of this representation using the binary system. We also have the hexadecimal system. Where do we use them? Hexadecimal system is used in computer system design alongside with programming. We also use these particular hexadecimal systems in web design, especially with the HTML and cascading style sheets, which we use the hexadecimal digits or the hexa digits to represent a color code when you are designing websites. They are the best in the representation of that, and these are direct HTML format. For example, when you want to change a particular color, you just vary red, green, and blue, the RGB color code, and out of that, you can be able to form different colors, like orange can be represented using this hexadecimal value, FFA500, which is a representation of red, green, and blue, the RGB color code. You vary the intensities of red, green, and blue, and you end up with a different color. So in website design, like I see in websites, you can have different colors in different sections of the website. You do that using the color code, which is represented using the hexadecimal format. Now, we'll get into understanding how to convert now from decimal to the various numbering systems that exist, which in this case we are going to refer to number-based conversion. And we'll start by looking at how we can convert a decimal number into a binary number. We have said decimal numbers are numbers to base 10, which is the language that we speak. Every time we add values using base 10, 10 plus 10 is 20, 30 plus 40 is 70. That is decimal numbering system. How can we convert those numbers into base 2, which is the binary number? So to do that, you divide the decimal number by 2 throughout, as you note the remainder after each division. Then you pick the values from bottom to top to get the required binary digit. You divide the numbers by 2 throughout after every division. We'll have an example. In this case, for instance, we want to change the decimal number 27 to base 2, to the binary. You divide by 2 throughout. In this case, we mean 27 divided by 2, you get 13, remainder 1, because 13 times 2 is 26. So 26, you'll have 2, remainder 1. Then again, that you divide 13 by 2, you get 6, remainder 1. Again, you divide 6 by 2, you get 3, remainder 0. You continue that way, 3 divided by 2, you get 1, remainder 1. 1 divided by 2, when you get such a case now, if the number you are dividing with is smaller than this number, you write 0, remainder that number. So in this case, 1 divided by 2 we write 0, remainder this 1. Then you pick the values from bottom to top. You'll end up with the binary value. So the binary equivalence of 27 is equal to 11011 base 2. Because it is a binary number, again, you'll end up with a base 2 number. Each and every time you divide a number by 2, you cannot get a remainder which is more than 1. Otherwise, that number, you can divide it again and still get a value. So you'll always get either a remainder which is a 1 or a 0 every time you divide a number by 2. We can do one more example for that particular conversion. 39, the decimal 39 into binary. Again, when you divide 39 by 2, you get 19, because 19 times 2 is 38. So you'll have remainder 1. This 19, you divide by 2 again, you get 9, remainder 1. This 9 divided by 2, you get 4, remainder 1. 4 divided by 2 is 2, remainder 0. 2 divided by 1 is 1, remainder 0. And the last step, 1 divided by 2 is 0, remainder this number. And again, remember, you pick the values from bottom to top, and there you get your binary equivalence of this 39. So every time you type 39 from your computer, because you have said computers only understand zeros and ones, it is converted into binary zeros and 1 through this process. So what is represented in your computer is 1001111, and not 39, because the computers are not designed to operate with decimal numbering system. They only display these because, again, the computer has a way of converting those numbers into the language that we can understand as human beings. Otherwise, if these particular values are represented in the computer, 10011, and we are not used to this particular language, we may not know what it means. But the internal functioning, the internal representation of data is in form of zeros and ones. And once you type a number, a value, or a letter, it is converted into the binary equivalence. Now, how does the computer now convert this binary into this decimal so that even it can be represented on the computers, that you can understand it? So let's look at how we can convert now back this binary into decimal. That's our second conversion. To convert a binary number into a decimal, you expand the binary digits using base 2 from the right side towards the left. You expand them using base 2. Then you add the values together. Once you add the values together, you'll end up with the decimal number that is required. What do we mean by that? You have a decimal number like this one, 100. You can represent it here, 100, 111, and then 0. So you expand them using base 2 from the right side towards the left. So the first digit, you represent them using base 2, 2 to power 0 times this 0, plus 2 to power 1 times this 1, plus 2 to power 2 times this 1, plus 2 to power 3 times this one plus 2 to power 4 times this 0, and the process continues until the last one. This will be 2 to power 5, 2 to power 6. So as you can see, the power of 0 increases as you move towards the right, from the right side towards the left. 0, 1, 2, 3, 4, and the process continues with as many binary digits that you have on this particular head, the power of zeros increases. So we multiply 2 to power 0 with this number, 2 to power 1 with this number, 2 to power 2 with the next digit, until the last digit. Then you add the values together. 2 to power 0 is 1, 1 times 0 is 0. 2 to power 1 is 2 times 1, you end up with 2. 2 to power 2 is 4 times 1, 4. 2 to power 3 is 8 times 1 is 8. 2 to power 4 is 16 times 0 is 0. 2 to power 5 is 32 times 0 is 0. 2 to power 6 is 64 times 1 is 64. Then you add these values together. 64 plus 8 plus 4 plus 2 plus 0. So this representation here shows the power of zeros increasing from the right side towards the left. 2 to power 0, 2 to power 1, 2 to power 3, 2 to power 2, 2 to power 3, 2 to power 4, 2 to power 5, 2 to power 6. With as many binary digits that you have, then you add them together. And therefore, the decimal equivalence of 1001110 is equal to 78. And just like we had done earlier on, to convert a decimal number into binary, we divided by 2. So if you convert 78 into binary, you end up with that digit. We can do one more simple example again so that you can understand more. In this case, we are going to do a binary number with a fractional part. This is 1010.1010. 1010.1011 base 2. To convert this into a decimal number, you expand using base 2. Now, from the decimal point towards this side, you expand using base 2. And from the decimal point, you expand them towards this side using the fractional base 2. For instance, like we have done this side, this will be 2 to 2.0, 2 to power 0 times 0, plus 2 to power 1 times this one, plus 2 to power 3 times this 0. And the last three, 2 to power 4 times this 1. Then you add the values together. So here you'll have 2 to power 0 is equals to 1 times 0, which is 0. 2 to power 1 is 2. So 2 times 1, 2, plus 2 to power 3 is 8 times 0, which is 0. 2 to power 4 is 16 times 1, which is 16. But from the decimal point moving towards this side, you'll not start with 2 to power 0. We'll start with 2 to power negative 1, because this is a fractional part, times this number. Now it will be times 1. Plus 2 to power negative 2 times this 0. Plus 2 to power negative 3 times this 1. And the process continues with as many digits that you have here. 2 to power negative 1, this is the same as 1 over 2 times 1. This is the same as 0.5 times 1. And the same case applies here. This is the same as 1 over 4 times 0. 1 over 8 times 1. You can move on and simplify them further. This is the same as 0.5 times 1, 0.25 times 0, and the process continues. Then you add them together. So this becomes the fractional part, this becomes the whole part. So you add up with a value like this one. From the decimal point, where we have the decimal point 2 to the power negative 1, 2 to the power negative 2, 2 to the power negative 3, 2 to the power negative 4, as you move towards this side. Negative 1, negative 2, negative 3, as you pre-multiply these numbers, this particular side you pre-multiply with the whole number, 0, 1, 2, 3, 4. Again now, because this was a fractional binary number, you end up with a fractional decimal, 10.6875 base 10. So that's how we convert a binary number into a decimal number. Now we have been able to understand how computers now convert the binary number into decimal numbers, and then from binary numbers into decimal numbers. Let's look at the second conversion, which is converting a decimal number into octal. How does a computer perform this? So again, like we have done with the binary, the decimal number is divided by 8 throughout. The decimal number is divided by 8 throughout, and then you note down the remainder after each division. And as we have done with the binary, again, you pick the values from bottom to top to get the required octal value. For example, if you want to convert 73 base 10 into octal, you divide by 8 throughout. So 73 divided by 8 is 9 remainder 1, because 9 times 8 is 72. You have remainder 1. 9 divided by 8, again it is 1 remainder 1. And 1 divided by 8, it is 0 remainder 1, because this number is smaller than this. So you have 0 remainder that number. So you end up again with 1, 1, 1. Another example, 675 base 10, we want to convert it to octal. You divide by 8 throughout. When you divide 675, divide by 8, you end up with 84, remainder 3. 84 divided by 8 is 10, remainder 4. 10 divided by 8, it is 1, remainder 2. And 1 divided by 8, it is 0, remainder 1. Then you pick the values from bottom to top, you end up with 1, 2, 4, 3 base 8. Remember, like we have done with the binary, when you divide a number by 8, you can get any remainder so long as it is between 0 to 7. And therefore, you put it under base 8, you end up with the octal value. Then how do we convert now that octal back to decimal? How would you go about converting this octal number back to the decimal number? Again, like we have done with the binary, you expand that number using base 8 from the right side towards the left. Now using base 8, not base 2, then you add the values together and you end up with the required octal number. We are going to have another example of that nature. So we want to convert the number 143, which is an octal, 143 base 8. We want to convert it into decimal. You have said you expand using base 8 from the right side towards the left. So this one will be 8 to the power 0 times 3 plus 8 to the power 1 times 4 plus 8 to the power 2 times this one. So as you move towards this head, you pre-multiply as the powers increase from 0, 1, 2. And if it's a fractional number, again, we do like we have done with the binary. You start with 8 to the power 1, if it's a fractional number, as you move this side. Then you add the values together. So 8 to the power 1 is equals to 1 times 3, which is 3. 8 to the power 1 is 1. 8 times 4, which is 32. Then 8 squared is 64. 64 plus 32, that will be 96 plus 3, 99 base 10. So you pre-multiply or you expand using this 8 from 0 as the powers increases, and as we pre-multiply with these numbers, then you add the values together to get the required decimal number. That is exactly what is in this particular table here. This represents the power of 8, 8 to the power 0, 8 to the power 1, 8 to the power 2, as we pre-multiply with these numbers here. Power 0 times 3, 8 to the power 1 times this 4, 8 to the power 2 times this 1, and we end up with 99 base 9. Another example, 586 base 8 into decimal. Again, you start with 8 to the power 0 times 7, 8 to the power 1 times 6, 8 to the power 2 times 5. Then you add them together, you get the required decimal number. The other conversion is, that is our last conversion for today. So that is the end of our lesson today. Once we meet in our next class, we look at the other number-based conversions, that is the hexadecimal numbering system, so that you can be able to understand the entire concept of how computers represent numbers within the data representation and the way they manipulate. Thank you so much.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.